Hi everyone, it's great to see everyone connected up. Today we're going to be talking about the new PSM-4. It's an online strength sensor and it gives you lots of advantages on your paper machine. But first, if you go to the little block on the right hand side, top of your screen, you'll see that you can enter bits and pieces and questions. Happy to answer questions during the next 20 or 30 minutes that we're talking about online strength sensing. If you want to just put in there where you're coming from, where you are at the moment, and we'll just check the tech, make sure everyone's connected and everyone's able to talk. So if you want to do that now, that would be terrific. I'll give you a few seconds. Great, we've got some people coming through now, which is terrific. Fantastic. Okay, looks like most of us are up and going. If you have problems, let us know and we'll try and sort it out for you. Now, today's webinar is really looking at it's a how-to webinar really. How to install an online strength sensor on the paper machine, how to make sure it's working properly, and then how to use it and get something out of it. And then ultimately, I guess, the thing to do would be how to save money. And that's what we all want to do on the paper machine. There's really two things we're trying to do. One is to make our products more consistently of a high quality, and the second is we want to do it to minimize our cost. So that's where we're coming from today, and that's what we're going to spend the next 20 or 30 minutes showing you. Okay, how to get the most out of your PSM-4 strength sensor. The PSM-4 strength sensor is an ultrasonic sensor. We've been using it for quite a while now. So we have lots of experience with it, and I want to share some of that with you. The PSM-4 strength sensor is a new upgraded version of the unit we've been using. So it has lots of features. We won't get into those now, but we're always happy to talk to people. So get in touch with us and we'll get back in touch with you and we can have a good talk about it. Now, like all these things, the first thing we want to do is talk about the size of the prize. What's in it for us? Well, there's a whole heap of things we can do with this sensor that's measuring properties continuously on the paper machine. Now, the first one is we can save ourselves time and trouble by minimizing our rejects. This is paper that's manufactured that doesn't meet our quality specifications or our customers' specifications. And on a typical paper machine, rejects and dealing with them and getting them wrong and getting them right, it's going to cost you about maybe $500,000 a year, $0.6 million a year. And that's from retesting, rework, shipping stuff out, getting it back, claims, all that sort of stuff. Online strength sensing allows you to control the quality and minimize the possibility of rejects. The second thing we can do is increase our production rates. And we do that by minimizing our variation. And that allows us to either use different input variables, or it also allows us to down weight. If we down weight, we can run the machine faster and still get the minimum result that we're after. The third thing we can do on some machines, especially recycled paper machines, is save starch. So on a typical paper machine, we would find that that's using starch either in the wet end or at the size press or at a speed sizer. Sort of starch savings we might see $1.25 million, something like that. Optimizing your furnish use. If you have options in terms of your furnish, then about $1.75 million. That's using cheaper furnish, replacement furnish, less refining, doing sort of things like that. And finally, the big one. The big one is if we can take a few grams off all our products and still get them to perform at a minimum level that we need, then we have big savings. And the sort of savings that are calculated on paper machines are around 10 million. Now that's a hard call. We know it's a hard call because customers buy often on weight. But nevertheless, that's where the big money is. That's what we should be pursuing. So that's the size of the prize. Let's look at how we go about doing it. Well, the first thing is, where can we firstly get some information from our PSM-4 measurements? Well, PSM-4 ultrasonic measurement, which is like a TSI measurement that many of us would have at our paper machines, they're sensitive to many processes down the machine. So here's a list of them. I won't go through them all. Some of the ones that we've had some success with are in terms of fiber quality, refiner control. MDCD is very important. It might seem like a small thing, but a lot of machines don't control it very well, and it directly affects the quality of the sheet and the variation of the quality in the sheet. MD draw straining is an interesting one. Size press, we're doing a lot of work on starch usage at the moment. Property reporting, Concora, and reduced reject material. How does a PSM-4 or an ultrasonic tester work? Well, we position it at the dry end of the machine, usually near the scanner, and it uses ultrasonic waves that travel through the paper in the CD direction and the machine direction. It turns out that the velocity that these waves travel through the paper are very, very closely related to paper stiffness. And this is the way we set up our online stiffness tester. We have a transmitter wheel which is contacting the sheet, and then a receiver wheel in the CD direction and a receiver wheel in the machine direction. And they're measuring different types of waves. In the CD direction, it's called a plane wave, and in the MD direction, it's called a shear wave. And a lot of work that was done at IPST and IPC in the States shows that these are all related together. And once you do the maths, you can pull out basically MD TSI and CD TSI. And Aurelia have learned how to use those measurements to predict the normal paper properties that we would use at the paper machine. One of the things we spent a lot of time doing is trying to design our sensors in a meaningful way, efficiently. And one of the techniques we use is finite element modeling. So here's a section of one of our wheel sections, and you can see it's being exercised and vibrating. It's how it would inject a wave that would propagate into the paper. So that's the actual model working. Here's a sort of a rendered version of the model with the wheel bending and vibrating. Now that's happening very quickly, many times a second, and of course not to that extent. That would probably be a good process on the paper machine. So this is an enhanced and enlarged, magnified version of the vibration. But you get the idea of how this sensor works. One of the other things that Aurelia has done is it's developed quite a lot of functional property descriptions. Now, functional property descriptions relate our measurement, the TSI measurement, to the sort of properties that you might want to understand, like, for instance, Concora, or CD ring crush, or SCT, or maybe even tensile. The PSM-4 functional property descriptions relate the elastic properties to the failure properties. So the example I've given here on the left is for tensile strength. That's a tensile strength test curve. And the elastic properties are the straight part at the start of the curve on the left, and they go to failure. What the PSM-4 attempts to do, and does very well, is relate those elastic stiffness properties, the TSI properties, to the failure properties that we're most interested in. The other thing that we do is that we don't just get a whole heap of data and try and relate it on a spreadsheet and correlate it. We try and develop real physical descriptions of the paper test. This has a big advantage because when things change on the paper machine, our physical descriptions of the paper test are still the same. So there's no need to go back to all the data and change it. Often when you're just using data and correlating, You could change something on the paper machine and all of a sudden all the correlations are incorrect. That doesn't happen with our predictors because they're based on the actual test descriptions that we use. The other thing that we notice from our experience is that this relationship between the stiffness, the elastic properties, and the failure properties, they're maintained for many processes that happen on the paper machine. So it becomes a very useful technique to quickly predict where things are going, what's happening to the quality of the sheet. For example, the sort of properties that are related very well are CD ring crush, MD ring crush, tensile, of course, Concora, and even some end-use properties like integrity of mediums on the corrugator. So there are lots and lots of things that can be done over a wide range of operation that are useful. We just need to understand what can be done and what can't be done. So in summary, what we can say is that the relationship between elastic properties and failure properties, which we need to predict properties from our test, is controlled by the fibre type and fibre quality. So that relationship will change if the fibre type changes a great deal. But the scaling, how much property is developed at any given time, is mostly controlled by the bonding achieved. And that's described very well by TSI measurements and our predictors. Here's an example. So in this case, we're looking at Concora. On the right, you've got our property wheel. So this gives you an idea of the sort of properties that we can generally predict. Things like CD extensional stiffness, pretty straightforward because it's closely related to TSI. But how about something like MD shear, which is a property that determines how well a medium will get through the corrugator, for instance? Or how about bending stiffness, which depends on geometry? All these things we have very good predictors for. The other thing we would say to people who are looking at this type of measurement is that when you are judging whether a predictor is good or not, always try and use the indexed values for the predictor. So always correlate the index values. So in this case on the left, for Concora, we have measured Concora index and predicted Concora index, and the relationship between the two for different basis weights on a paper machine. And the reason we like to use indexed values is because when you relate them, you're really relating the material property and not the basis weight of the paper, which of course will change the property values. So index values remove the effect of basis weight, and you're really looking at real predictions of property. And they can be translated to any basis weight you like, so much more convenient. Here's another example, short span compression test, which is becoming very popular at the moment because it's relatively easy, although it's a little bit noisier than, say, the CD ring crush test statistically. Nevertheless, it's much easier to do and it can be automated. But we can measure that continuously on the paper machine with the PSM-4. And here's an example for those weight grades that we have. Lab measured SCT versus predicted SCT, and you can see that the correlation is excellent, even within a basis weight range. So let's have a look at how we would go about installing one of these systems. Is it easy or hard? Is it complex or simple? Well, let's have a closer look at it. And there are really 4 stages to how we would go about this sort of project. One is we would install and set up. The second thing is we would validate the sensor operation. And usually we do that against property. Thirdly, we would characterize the machine. It's always good to get information back quickly about how your machine is going. And finally, we'd identify savings and benefits, which of course is one of the main reasons why we want to do this sort of work. So let's have a look at those in a bit more detail, and I'll give you some quick examples of how we do that. So, strength sensor position. Well, normally, and I've given you an example of the old strength sensor, which was on a US paper machine as an example for a few years back. And on the left is the newer version, which is going to be rolled out in a few months' time. Generally, this is a single position sensor. So it's bolted to the ground and it measures 1 point across the width of the paper machine. It really is very simple to install. We measure the height to the web under the position that we're going to put the sensor, and then we get the mill, usually, depending on where they are in the world, to build the pedestal floor mount. And you can see that on the left-hand side under our sensor column and head. So the pedestal floor mount is built by the mill and it's bolted into the floor in the position that we've decided the sensor is going to go in. And then when we come and install, all we do is bolt our head and column into the top of that with 4 bolts. So it's very quick. So within, say, 30 minutes or so, I would expect that the mechanical part of this installation would be done. So a short shut would do it, although generally, to be fair, I guess, we prefer to do it at a longer shut, a maintenance shut, because then we have facilities available to us. The old system used to wire the measurement back to a control box. The new system, which I'll talk to you about in a second, uses Wi-Fi, so it's even easier to set up than it was. So here's a schematic of how the system would work. You have the pedestal bolted to the floor, you have an actuator and a sensor head, and the sensor head contacts the paper web at the angle that the paper web is coming through the machine at that point. The 2 orange blocks to the right represent the scanner. So generally we would be close to the scanner, but not necessarily in the same web position. We measure the web height. We do that independently and separately. Sometimes we come out, but sometimes we just take advantage of mill personnel. And then when we come out, we adjust in the past, we've adjusted the head to the web. The new version will do that automatically. So it makes it a lot easier. And also once we get onto the machine and the paper sheet comes back onto the machine, then it will automatically adjust its position to give the best result. We find that that's much more convenient. So if we step back a bit further and look at the whole system, our connections are generally either wireless or Ethernet. The PSM-4 itself is in the machine, and then it's talking to a control box, usually at the front or back of the machine, which has the power supplies and some manual controls if we want to lower the head or change the head manually. And then they both talk to a server which we place in the machine control room, and you can see that on the left bottom side. And generally, especially for demonstrations and projects where it's not a permanent installation, generally we will use wireless to connect them all together. So there's no need for project work or getting a project team together or getting contractors to the machine to wire it up. It all goes together seamlessly from that point on. So we install, we set up the comms, and then we're up and going and ready to get going. So that's one of the advantages of the new PSM-4. Our experience with this technology, probably pretty important. In our experience over many, many years, we've seen no sheet marking, even though it's a contacting system. It's caused no runnability issues. Generally, we don't require any cleaning, just apart from the normal wiping fiber off the surfaces, but the contacting surfaces themselves are kept very clean. And in this instance, we had no maintenance required for 13 months. And that's about our typical experience as well. In this case, it was a US craft linerboard machine that we were doing work on. So let's go to sensor validation. Well, here's an example of sensor validation. We're comparing the laboratory CD ring crush values with the PSM-4 CD ring crush predictor. And again, we're using indexed values. So these are real material properties that are changing. We're not looking at grade changes here. So this is following real material changes in property. And you can see that the relationship between the PSM-4 result and the lab CD ring crush is very useful indeed. And certainly you can follow trends very well. In this case, we weren't adjusting the result for moisture. The next step in the process would be machine characterization. Now, we do lots and lots of things around machine characterization. How variable is your machine compared to other machines? How variable is your machine compared to competitor machines? How variable is your machine on different grades? There's lots of things we can do. How can we optimize the paper grades you're making? How can we save costs? What's the cost compared to others? There's lots of things we can do in terms of characterizing your paper machine and benchmarking it. But I thought this would be of interest to people, the way we've presented this data. This data represents the property variation peak to peak on the paper machine. And typically on a paper machine, there's probably 20 to 25% property variation across the whole machine. And what I've done here is I've divided that variation up into fractions or percentages that represent the time scale of the variation and the type of variation. And then what we're going to do is say, how would we solve or improve the variation that we see? So hopefully that makes sense to you. So on the y-axis on the left-hand side is time scale. And that's talking about how fast does the variation occur. On the bottom axis, periodicity, that's the x-axis. We're talking about, is the variation periodic? Does it happen again and again in a cyclic way? Or is it non-periodic? Is it just sort of wander around? And once you've measured what type of variation you have, you can apply different strategies to it. So on a typical, an indicative paper machine, for example, very fast but non-periodic variation represents about a third, 34%, the orange part of the variation that you would see on the paper machine. And to fix that, you would need to get some new capital equipment and maintain what you've already got, because fast and non-periodic is really a signature of the paper machine age and technology that you're using. If we go diagonally down to the green area, that's only 12%. And that represents periodic variation that's slow. Now, we like slow variation, and by slow variation, I'm talking about, say, something that's slower than 20 minutes. Because slow variation means with our sensor, you can go back and control it out. So slow variation that's periodic, identify the trend, use the online measure to see what you've done and whether you've improved the situation, and control. And generally, you'll need a project team to identify the source and remove it. Let's move to the left. That's the blue part. Around half, in this case 46%, of the variation is slow and non-periodic. This is terrific. This is a great thing for us because it means we can control it out with levers we already have on the paper machine. That's terrific. All we have to do is measure that it's happening, and that's what the PSM-4 does. So for slow, non-periodic variation, we identify the trends as they happen in real time, and we control it. And down the track, we manage input variation, which is where this type of non-periodic variation comes from. And then finally, up in the right-hand side, right-hand top, the gold area, about 8% is fast and periodic. And that's good too, because what that means is we can find out around the paper machine what is varying in a periodic manner at the rate that we're seeing on our online sensor. So in this case, the project team identifies the source and removes it. Control system errors and operating instability, they're improved and fixed. So that's one example, just one example of how you might apply the sensor to characterize a particular paper machine. Finally, we want to identify ways of saving money or improving quality, or both. So here's some examples of how you might do that. In this case, we went to a mill and they were having trouble controlling their MD/CD ratio, their rush drag. Not only controlling it, but really knowing what it was at any given point. And here's an example. The blue lines represent the lab measurement and the red lines represent the PSM-4 measurement in an earlier model. And you can see a picture on the left. It was a 100% recycled paper machine. Now, the big advantage here is that within 1 or 2 days, we were measuring MD/CD ratio and had been able to lower the value that they were operating at in general from around 2.4, 2.3 down to around 2. Because they were chasing CD properties, that meant that they got improvements in CD ring crush in 2 days of 3 to 4%, or CD SCT of 4 to 5%. And they've been able to maintain that control since. Now that's worth a lot of money because you can take that improved 3 or 4 or 5% and you can either save money with it, improve your product, take starch out in this instance, optimize the system, improve your production rate. There's lots of ways of taking that advantage. The second example is an example I love, and you might have seen it before. I really like this example, so I'm going to use it again. And you can see here that across perhaps 8 hours maybe, there's been some variation and it's cyclic. So this would be an example of fast cyclic variation. The blue trace is CD-SCT as measured by our PSM-4 online. And it's a 12-minute cycle time roughly. And it's always there. You can see it. It just keeps going. And the thing I like about this is that at about 8 a.m., where that red dotted line is, there's a shift change. And the person who comes in, the operator who's in charge, within, it looks like seconds on the screen, changes the operation of the machine, removes the periodic variation, and raises the level of the CD-SCT value back to its average. So we pat him on the back, but it's a great example of how if you're not aware, if you don't see it, you're not going to be able to do anything about it. In this case, if you look at the green trace below it, which is the MD/CD ratio, you can see that it was the MD/CD ratio that was varying as shown by our PSM-4. This was on a European recycled paper machine. I think this is a final example of how you might use the PSM-4. The blue and the green traces represent the PSM measurement, an older version of it, and the lab measurement. So the blue is the online measurement, continuous measurement, and the green is the top of reel lab measurement. And then the gold, which has its axis to the right of the plot, the gold trace is the amount of broken waste that was added, broke and waste that was added to the sheet at any given time. And you can see that the PSM-4 continuously monitors the effect of adding less or more broke and waste. Now, the outcome of this result, of course, is that they have considered putting in a control around how much waste and broke that they add at any given point. So basically, to control their quality, they need to manage the addition of broken and recovered fibre. And it's very easy to do if you're measuring it every second of every day. So, we're getting to the end of this webinar. How to get the best out of the PSM-4. You put the PSM-4 on, or you're thinking about it, the first thing to do is set aside an internal champion on your site. our experience is that if there's no one looking after this as a project, things tend to fall about. So it's very important to have someone who's enthusiastic and has responsibility for getting this project up and going. The second thing you would like to do, that you must do, is identify a strong project or issue. So identify a project that excites people at the mill, that's going to have an impact on the mill. Either a customer challenge or an internal issue that's always been a problem, and use that to show that this technology is valuable. Start working on an initial joint project with Aurelia using this technology. And finally, the third thing you need to do, take advantage of our experience. We have expertise of paper machines. We have information that other people don't have because they've never been able to measure in this way continuously. Take advantage of it. We offer project consulting. We offer help when we install PSM-4s. Take advantage of our information, techniques and technology, and you'll find that these projects can pretty much be brought to heel very quickly. So there you have it. Hopefully that's been of interest to you. The PSM-4, the new upgraded version, will be available in a month or two. The old version is available currently. Either way, there are big advantages in using a continuous property measurement on your paper machine. If you need some more information, just contact us. We're happy to talk about this stuff. We're excited by it. So hopefully we'll hear from you very soon. Have a great day.